Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 28, part B. We are in regression. This is going to be part 2 of chapter 10 in our textbook. Let's go ahead and get started. So this was the easy equation to solve. Now let's look at the tedious one for beta 1 hat. All right, so we do the same thing. We take the derivative, but now with respect to beta 1, and we set that equal to 0. And so, again, we end up with, because this term, this is the term inside that has beta 1 in it. It is a negative, but we don't just end up with a negative 1. Xi is a constant. So when I take partial with respect to beta 1 of negative beta 1 xi, xi is a constant with respect to beta 1. So it's going to be xi partial with respect to beta 1 of negative beta 1, which is going to be a negative 1. So I get negative xi. So I've pulled the negative out to the side, outside of the summation, and then xi is multiplied by everything that's left once I subtract 1 from the exponent. Okay. And then I use my summations to rewrite the equation, and I get this. So I can distribute my summation, but notice I have an xi in all three terms. In fact, xi squared, because I had to multiply, I had to distribute this across every value. Okay. So this is tedious, and there's a trick to it. So I'm solving for beta 1, the term that has beta 1 in it. And then I'm going to rewrite, let's see, what did I do? I rewrote beta naught as its solved value up here. I substituted in y bar minus beta 1 hat x bar right here. And so then I distribute that. So I've distributed it. And then I pull all the terms that have beta 1 to the same side. So now I have this minus this, and I have this quantity. And what I can do is I can factor out the beta 1 from both of these, and that's what I've done. And then I have a trick. I add and subtract n times x bar y bar. I add and subtract it, so I'm adding and subtracting 1. And then I multiply, so remember that x bar is 1 over n sum of xi, and y bar is 1 over n sum of yi. And so for one of the, actually, so what I did is I've left this, I've changed this one, since there's no i's in this quantity, I've just changed it to a sum from I equals 1 to n, so the n times there. I've done it in reverse. And then for this one, I multiplied the n times the y bar. So if I multiply n times y bar, I get the sum of yi. And so now I have sum of xi, yi, then I have the sum of y bar, xi, minus the sum, and then minus the sum of x bar yi, and then I have the sum of x bar y bar. And so when I can then pull the summation out to the outside, and then it turns out that I can factor it this way. So I've now factored this by using my trick of adding and subtracting the same value. I have now made this as a sum of a product. So xi minus x bar, yi minus y bar. Okay. Now I divide both sides by this term here. Okay, to get the beta 1 by itself, it becomes beta 1 hat, because now it's estimated using just x's and y's, which are the sample. Okay, and so on the bottom, I'm now going to do the same thing. I'm adding and subtracting this value, and then I'm being clever about it so that I can then rewrite it, you'll see, as the sum of xi minus x bar squared. This equation is the equation I want because this is the easiest way to calculate this expression. All right, the easiest way to calculate it. So quite a bit of algebra involved in this. It's not hard, it's just tedious, and there's a trick. Okay, so please take a look at this and make sure that you can work through it and understand. But we end up with this equation that's in the box here. Okay, so now we have the least squares line is y hat is equal to beta naught hat plus beta 1 hat times x. Or we can write it as y hat is equal to y bar plus, substituting in for beta hat naught, I can end up with an equation in this form. So, and what I've done is I've substituted this in, and then I've combined the terms that have beta 1 hat in it. And so this is an equation that we use quite a bit, which is y hat is equal to y bar plus beta 1 hat times x minus x bar. So if I wanted to put i's in here, I could, okay, for each observation or each pair, okay? All right. So, sum of squares of error. These are defined as yi, the actual value of y, minus its residual. So, and then that quantity squared, and then I'm summing, to get SSE, I sum that up. This is the same that we've seen for the ANOVA models. This is an analogous way of looking at the same thing. Okay. One of the differences is that we're assuming that x is a continuous variable in this case, or it's a quantitative variable. It's not a factor. Okay, so that would be the big difference. So the estimates of beta naught hat and beta 1 hat are called the best in the sense that the following inequality holds for any beta naught hat and any beta 1 hat that we would choose. Any estimators, we're using a star here, so beta naught star, beta 1 star, as an estimator. So any estimator we could come up with for beta naught and for beta 1, this would be true. That the sum of squares, so I'm sorry I missed the square here. There has to be a square. So the sum of squares of error is yi minus beta naught hat plus beta 1 hat xi. That's going to be less than or equal to the same equation with any other estimator of beta naught and beta 1 that we could come up with. So this inequality is always true. It's the minimum, so it's the best in that the sum of squares has been minimized. It's minimized by beta naught hat and beta 1 hat that we derived. Okay. And that's why it's called the least squares method, because it minimizes the sum of squares error. And I am going to, actually, what I'm going to do is put that in red so that when I come back to correct my notes, I will have it easily to see. Okay. Now let's talk about estimating sigma squared. So remember that we have epsilon as a normally distributed quantity, random quantity, with mean 0 and variance sigma squared. And SSE is the sum of yi minus yi hat squared. If the straight line model is appropriate, then we can estimate sigma squared by. So this is a very, very important statement. If the straight line model is appropriate, then we can do this. So if it's significant, then we can do this. And we'll talk about testing whether it is. So, but it's only this estimate is only any good if this model is significant or is valid, if you want to say that way. Okay, so we're going to say sigma hat squared. We're going to use some notation. S squared of S sub y given x squared, that's another notation, is also estimated the MSE. And so we've seen that in the ANOVA, that it's the sum of squares error divided by the degrees of freedom error. And it turns out that our degrees of freedom here is, in the straight line model, is n minus 2, because we're estimating two parameters. Okay? So beta naught and beta 1. So we have 1 over 2, 1 over n minus 2, sum of yi minus yi hat squared. All right, and so I've said that about, this is not a very technical explanation, but we are estimating these two parameters, so we need to subtract 2 degrees of freedom. All right, hopefully we'll have time to get to the technical explanation of this. Okay. Now, let's talk about some inferences about the slope and the intercept. Before we can do this, we have to talk about the sampling distribution of beta 1 hat. If you don't remember what the sampling distribution is, please look up, it keeps getting bigger, Khan Academy video on sampling distributions. It's a short video, it's not very long at all, and it might be very beneficial to you if you don't remember or recall sampling distributions. He explains it very well, okay? So let's talk about beta 1 hat. We're first going to take the expected value. So we take the expected value of this lovely quantity that I'm sure makes you very excited, but this, let me be specific and help us out here. Well, x is a fixed value. So we're taking the expected value with respect to y, only with respect to y, because x is fixed, not random. So remember that the expected value of a constant is the constant. All right, so this is e of y. Now what I've done here is, because this bottom is a constant, it's all x's, so it doesn't play into it. And this quantity here, those are all x's, so those are constants. So the only variables that I have here, may have, are yi actually, because y bar is a constant. It's just a number. So what I've done is I've distributed the y's here. I've distributed this times this, and I've taken this times this, and so that's what I've written out here. I've got xi minus x bar times yi, and then I've got xi minus x bar times y bar. Well, when I take the expectation of this, this actually, see, remember it's a constant, but I have, so let me write it out, expectation of this side, and now I have xi minus x bar, okay, times yi. All right. Now, I have to be careful because here, y bar is a constant. When I pull y bar out here, the sum of xi minus x bar is always 0. Always. Okay? So that's something we learned in, I hope, in elementary statistics. Okay? So I have a constant, so that can come to the front, and then this term comes to 0, so that whole thing is 0. And I'm left with this other side, and I have Now what I can't do is I can't pull yi out. I can't do that because it has an I. So because it has that subscript, it stays in. And so I have the sum of, for every value of x, I have xi minus x bar times the expected value of yi. Okay, so I can't, this does not cancel out to 0. And I can't do anything with the top versus the bottom here. But I can rewrite the expected value of yi as beta naught plus beta 1 xi. Okay, so the expected value of an estimate, if it's unbiased, is so the expected value of beta naught hat is beta naught, and the expected value of beta 1, but actually I don't need to, yeah, so the equation for yi, the expected value, is this equation. Okay, so let's keep going. I'm going to clean up pretty quickly here and then move on. Okay, so now I can again do the same trick where I'm distributing this quantity times that. So I've got beta naught, sum of xi minus x bar, beta 1, and again this quantity is 0. But here I have the extra xi, so it's not 0. So I end up with this quantity, and now I'm going to complete the square using my trick of adding and subtracting n times x bar squared. Okay, and when I do that and rearrange, I end up eventually with the sum of xi minus x bar squared over the sum of xi minus x bar squared, which is the same quantity, all multiplied by beta 1. So the expected value of beta 1 hat is beta 1, which is what we would hope. And so it's an unbiased estimator. So that is always nice when our estimator is unbiased. It's equal, the expected value is equal to the parameter. All right, that's it for this video. If you have questions, please make sure you come to virtual office hours. If you need help prior to office hours, by all means email me. But when you email me, if it's about a problem, then email me what the problem is, because I may not have it available, and then your work on that problem so far. If it's code, then by all means send me a copy of the code, and in the email tell me where you're having the problem and that you need help. And I will get back to you as soon as it's possible. Please take care of yourself and stay safe, because we want to see you here next time.